It's a plugin. Okay, so here exported spec equals export dict. Previously, this was a input type definition where so basically we're within input right now. Ah, okay. Oh no, we're within definition. Okay, so we're within definition. We want to define the spec. So what is this? This is the schema for the manifest, right? What's the schema for the manifest? Is the DID method, right? All right. So schema for the manifest, DID method. Okay, so it was my. Can you hear me? Yes. All right. So great. Let's import the plugin. So what do we do? Well, this is exporting it. So what are we trying to do here? Basically, spec. Spec. Yeah, I think, yeah, I think that this is just another version of entry point. Oh, oh, this solves this. Again, here it is. It's the this is we found it. This is the shared config solution, I think. So we, yeah, this spec is the shared config solution. So, oh, okay. So basically, we have the plugin. So we shouldn't be. This was all based on named tuples at first, and this input stuff just didn't evolve. Yeah, no, the input stuff just never got hooked in with the plugin stuff when we redid to the do the double context entry and the config. Okay, so we just need to make spec a plugin. That's all we need to do, which means, oh, perfect. Okay, so um, um, which means, so we just need to make spec a plugin. So need to do make, before I forget, oh, that's why we have the recording. Make spec a plugin. Okay. Okay, good. Okay, yes, I'm glad I wrote that down. All right. Um, so let's see. Well, great. Let's do it. Okay, so how do we do that? So let's turn on some line numbering here. What is that thing running over there? So that's running the system context. That's right. Okay, so and then the system context got tripped up on this. Well, this is going to be great. Okay, so and remember that everything just got simplified a lot, right? Um, we can basically everything is the system context. Um, System context is the upstream, the overlays, and the orchestrator. And and oh, the okay, one thing on the time travel thing. So um, the I was trying, I was going somewhere with the things of consciousness and overlapping states of consciousness. So effectively, um, uh, okay, so if you're going to time travel, right, what's the first thing you need to think about doing? You need to think about speeding up, right? Because we either need to go backwards or we need to go forwards, right? So, um, I mean, if we're going to treat it like anything else, so we might as well, right? So, let's assume that we can go only forwards. Let's just assume we can only go forwards, and that if we can go forwards, we can loop back around and we can, uh, basically integer overflow. And if you saw me playing with the OBS filters, there you go. Um, so uh, so Yeah, basically, we need to think about how do we go faster, right? And so, how do we go faster? Well, we go faster when we agree that reality is going faster, right? So, this is the consensus shift stuff. So, if we all agree that reality is going faster, then effectively we're going faster, right? So, if let's see. Yeah, okay, so it's relative. So time is relative because time, think about it, think about your life. So over the course of your life, you have more and more experiences, more and more system contexts, right? And so time appears to go faster, right? It appears to be like it feels like that was just yesterday, like, or it's time, yeah, time. It starts to speed up, right? Because there's more system context. Well, how do you make time slow down? Well, you switch and you. Okay, it has to do with operating on inference. Where was it? Operating on an inference versus. Okay, so if you can spend as much time as possible within the or you can if you can you want to trigger as many conscious states in parallel at the same time. So the more conscious states you have in parallel at the same time, the more the more parallel conscious states. So parallel conscious states allow for an oversubscribed system where data and compute are represented in this heterogeneous way, right? The Web3 format or the neuron format within your brain, right? So we basically can have like this acceptable losses sort of thing because this system is redundant, right? So basically, by defining policies, right? So these are our provenances on our strategic plans, right? So, but by defining dynamic policies around the provenance of our strategic plans, we can ensure that a fail-safe set of conscious activities, conscious trains of thought, which are running as subflows within the top level executing system context effectively data flow, then we can effectively what we have is this acceptable risk mitigation from various sides, right? And this is what allows us to basically say, okay, some pieces are going to operate on inference right now for this next tick, and some pieces are going to, go directly into training, and some pieces are going to go, um, it- like, let's see, like, it's basically just like your brain and Alice's brain now, in effect, is doing this thing where it's like it's this best guess, right? It's okay, so things are live, right? And you're in a live environment. We understand, mistakes will be made, right? Packets are going to get dropped, right? Because an oversubscribed system is a system at um, peak communication or peak learning. Um, so in this is a hypothesis, right? So the hypothesis is that an oversubscribed system learns faster and it doesn't it's not that it learns the key thing here is that okay, so the key the a piece of the okay, so hypothesis. So uh an oversubscribed system. Fuck. Wait. An oversubscribed system. An oversubscribed system. Okay. Oh, yes. So an oversubscribed, remember, Alice begins to think more and more strategically, right? So an oversubscribed system, if these trains of thought are distributed in the, um, in the right areas, uh, the cohesion, like this shared consciousness, this cohesion between strategic principles of aligned system context across different contexts within which one is operating, um, uh, it allows you to kill two birds with one stone strategically. And when uh, you know uh, difficult problems become easy problems, so long as you can think and act strategically. If you don't have both action and um, if you can't have the action is where the risk mitigation comes in, right? As well as the action is where the risk mitigation comes in, because it does us no good to think unless we have some idea of what the result of acting on our thought would be, right? We really that would be irresponsible. We need to understand what is the risk of each potential decision, of each execution, of each system context, of each thought, right? And this is why we're keeping our chain of information and our provenance information and all of this, right? So we have this unbroken chain by which we can make decisions. So, okay. Oh, yeah. So the aligned states of consciousness really just represent these patterns that are seen across aligned like pools of assets, nodes or clusters of nodes or agents or whatever that just function, particularly well at different things when you put them together. Right, for whatever reason, and we don't need to care about why, right? And basically, we'll make Alice care about why, right? But we won't care exactly why. We'll just know. We just say, you know, we understand. There's a lot of different variables, right? When you're out trying to get something done, but keep these things in mind. Like, what are the strategic principles? What are the strategic plans that we're overlaying? Um, and do your best to solve these problems, right? And so when we give her a problem to solve, she what were we doing? What were we saying? We were saying something about she okay. When she goes, yeah. So basically, if we can teach her strategic principles and strategic plans, then she can effectively think strategically, and yeah, so then with good communication, another hypothesis is basically that with good communication any problem is easy to solve, and so or at least determine whether you can solve it or not, right? And where's the docs, right? So if you have all the docs and all the docs are clear and everything's validated, then well, you can probably figure out right away whether this is going to be easy or hard problem to solve, right? It may have already been done, right? You just do it. You just call the function. So, okay, so what do we? Let's just do this as a plugin. Let's just get this done. I need to stop talking. So, all right. Okay, yeah, just get out of here. What is that? Okay, yeah, sure, you're good. Okay, I love NodeMon. Oh my God. Although it has produced like this level of reward feedback loop addiction. So that could be, I mean, I think it's a good thing. I think this is a good thing. So I think there's nothing better than a massively parallel reward feedback loop. That's what I've learned from NodeMon and Fan Notify and that family of file watch utilities. So my hard disks do not thank you. I have burned a lot of different hard disks on this. Because I just hit save because I love to watch it rerun. It's so satisfying. Every time you save the file, it'll rerun the whole thing and whatever you tell it to. It's great. Um, and this is basically, you know, uh, well, so here's obviously here's some inspiration um, for running everything in parallel uh, all at once on every change, right? So basically, what we're shooting for here is Node Mon on steroids. Um, it's gonna be fun. Um, okay, so okay, okay, focus. Okay, export spec, make spec a plugin. Okay, let's do it. Boop and okay, so export spec equals entry point dot load. Okay, so what's happening here? Where are we? Export. Do. We're at definition. We want to export dict. The correct thing for definition to do is exported spec. So we should just be doing, you should just be doing export and then whatever the self.spec is. All right, so that'll take care of that. Done. So now that's exporting. So now we got to go in the other way. So this, 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 this is bad. So that's bad. Yeah, I should have had a clue that this was we were going in the wrong direction here when we were digging into internal Python code to call things with multiple underscores and create classes with yeah, certain things should be difficult and certain things should not be difficult, and this was probably more more hoops. Should have been a signal then. Um, we shouldn't have jumped through this many hoops. But this stuff evolved over. No, we didn't even. No, yeah, we did. Okay. Let's just delete all this. Yeah, it says it right here. All right, this is horrible, but bear with me. That should be reworded to say, "This is horrible. Please, someone question this." Um, we should avoid copying here, I think. Yeah, probably, but we're not going to change that right now because we're only changing spec. So if spec in kwargs. All right, so what is this? From dict. All right. Let's see. So if spec in kwargs. So spec is in kwargs. It better be something we can create a plugin out of. So what would make spec set? So let's just double check here that we know everywhere that would check, that would set spec. Yeah, grab spec equals. Okay, yeah, so I think it's, yeah, mostly this auto definition stuff. Okay, where's that in use? Everywhere, just like everything else. Okay. What's this space? What are we trying to get to? Types. What's types? Is this types? No, this is entry points. This types. That's man. This looks like entry point. No, that might be operation types. No, that's entry point. Where's types? Is it even open? No, this is types. Duh. Okay. That always happens to me. Oh, that's right. We moved this in here. Okay, so that's what threw me off. Okay, so inner class in primitive types. Once we get this thing, remember we're in the middle of writing. We're in the middle of writing a example, um, which is going to uh, back up the thread because all this stuff we're going to reuse immediately when we get to the CV event tool thing. So inner class and primitive types. This is how we're going to do the whole thing. So basically, we're going to have this like, Alice is going to be like this, effectively, she's ephemeral. She's this ephemeral living entity because she lives on the chain. And so if something picks her up and wants to execute her, basically herself, right? So an implementation of her in the runtime format sees an implementation of her in the serialized format, which is, AKA the open architecture, right? Then she can just execute it, right? So she's like, she exists and she doesn't all at the same time because she only exists between tick and talk, right? And now she exists between tick and talk everywhere where she's running. Um, so, effectively, I guess, for whatever those snippets in time are, she exists, right? So, okay. Um, Inner class, all right, okay. The annotation the form, let's find it. Semi-class, get origin, parameterizations list, okay. Okay, so we can drop all the primitive stuff. So let's, okay, no, let's not go drop all the primitive stuff right now. We should drop all, no. We should drop all the primitive stuff. Definition. We should drop all the primitive stuff. We should drop all the primitive stuff. Why? Because a definition is a specific type of input. Okay, so we'll drop all the primitive stuff. Drop all the primitive stuff. A definition, just like a system context, is actually, a definition is a system context. A definition is a system context. Drop all the primitive. A definition is a system context. Because we can load all these things dynamically with the overlays now. So everything can be dynamic. Definition and context aware. So when a definition is created, okay, so a definition, let's just play with this for a moment. Is a system, is input. An input is just a DID, basically, is what we'll map it to. To be a system context, I believe it will have to be a pure DID. No, it could probably be just a DID as well. You could have just a DID. That's a system context because you could alias off the method to some other lookup system like we were playing around with the GitHub key, shared key system, right? So you could have, effectively, you could have a system context, right? So you could say, I have an input network, which on startup grabs inputs, or what? Okay, so you could say, I have a startup operation, right? An auto start operation, which on start grabs the, or let's see. Yeah, basically, if you see this DID, the thing with the GitHub stuff was if you see this DID, then you can look up this SSH key, and then you could, in GitHub, and then you could confirm that it's the same key, and you could then use the comment field to like trampoline into something else from there, right? But you could use that as your root of trust and your deployment mechanism, therefore, right? Because all you would have to do is pass a single DID for a GitHub key, and then you could look up, yeah, you could look up the other side on GitHub, and then you could go to the repo and you could look at the GPG verified signature. So then the question becomes, no, you could use the GPG verified signature, but you can't, can you sign, can, please, come on, can you, okay, okay. So you can take a DID and you can look up to GitHub. Okay, given just, look at this. All right, this is fantastic. These Web3 people have been doing fantastic work. Okay, everybody has been doing fantastic work. Everybody has been doing fantastic work. Okay, because the TPM people have also been doing fantastic work. All right, so um, we can um, we can have a DID. We can have a DID. Okay, we can have a DID. DID, GitHub, key, uh, whatever. Um, or maybe let's github.com/pdxshiny.pub. Nope. What is it? Hmm. How does this work? Dot key. Dot keys? Yes. Dot keys. Okay, so username dot keys. So we hit username dot keys. What can we use here? We can use, aha. Okay, so we will use, oh no, we already have the key. Okay, no, but we don't want to do that. We got to scan. What are we going to do? Compare all the keys? We could just compare all the keys. Let's just use the comment field. Okay, so we can, I was going to say use the comment field. We're just going to put two things in the comment field. We just encode something in the comment field, right? So say, for example, we put a base64 encoded, or we just put, yeah, say we put a JSON blob or a base64 encoded CBOR blob at the end of this uh, key, right? One of the keys. We could, maybe put a tag on the front of that that's like, tag colon, then the base64 encoded blob, right? And then we could look up by the tag, right? So we could say DID GitHub key PDX Johnny colon my tagged key. There we go. All right. Or let's see. Let's say example DID example key. Okay. So now let's make a mermaid diagram. No, let's not make a mermaid diagram. I'm not going to be able to figure that out. I always get lost. Okay, so we'll write everything down. The process that I usually follow is basically write down everything you know, right? And then everything you know how to do anything with. And this is basically the same. I mean, this is just the same thing, right? And so you just enumerate all your assets and all your processes, and then pick the ones that seem best, right, given the constraints of the system, of the problem, right? And you do your best to remember what you can, right? And that's what else will do too. So, okay, so DID GitHub key, PDX China DID example key. Okay. So that would mean, yeah, basically we end up with one of these keys. It says DID example key and then colon this base64 encoded CBOR blob. Then we can put whatever the hell the data we want behind it, right? Okay, so the data that we could put behind. Okay, so no, we're not going to do that. That's right. Okay, so we're going to do DID example key. Yeah, DID example key. Okay, so on the other side of this thing, let me just put it here because I'm getting confused. Okay, so let me. Okay. Okay, here, set no paste. Set, oh, set paste. Okay. So here, all right. So so this is the DID, and this is the SSH key. Let's make it markdown. Example. Example of, I'm not even sure what we're doing. Definition input, definition primitive. Oh, minimal. Oh, wow. Oh, okay. This is what we're doing. Where were we? We were over here writing something, weren't we? No. Oh, yeah, we were writing this. Drop of primitive stuff. Definition of system context is an input DID. Okay. So minimal trusted execution deployment. Right. So this is our minimal trusted RCE or whatever deployment, right? Basically, hey, I want to throw some code over the wall and see it stick. Can you go grab that from GitHub for me, right? Can you go grab the latest thing? Let's just assume we're distributing via GitHub. We can distribute via whatever the hell we want later, but right now we're just going to assume that we're distributing via GitHub, right? So this is So DID example key. Okay, so what is this thing going to do? So let's make this a little more interesting and do another jump here. So I was going to say jump example key directly to project, but let's maybe do like directly to asset. Let's do key. So example. Okay, so let's see. Okay, so frequently an issue that I've run into with GitHub's SSH key support is that you can't restrict it to per project or per branch, right? So we're going to basically, I mean, basically what we can use these DIDs to do is throw arbitrary levels of RBAC on things, role-based access control, right? So we can, and we can construct effectively like these we construct these webs of trust for our own assets, um, and then we leverage like this proxy system, effectively being the DIDs and the operations, and it works like OIDC. It's like OIDC for Web3, or basically OIDC for everything, because you can proxy everything between OIDC and Web3, and that way things that don't speak HTTP can still do OIDC based auth because they can speak DIDs, and we can map DIDs to OIDC and claims, right? So in flies the DID, and it says GitHub. Okay, so GitHub exec. All right, so we want to execute some code from GitHub. All right. Uh, Remember, we have a input network which saw this thing, somehow saw this DID come in, right? So it's got a new input, or wait a minute. Okay, yeah, so this DID comes in. Okay, this DID comes in. It is a piece of code. It is a piece of code. It has reference to a piece of code. We're going to run a system context. We want to execute a system context. What do we want to execute? We want to execute either, we want to do we want to do a state change, right? So a state change could be go from not remembering this to remembering this, right? So give me some data that you just remembered, right? So other agent, please pull from memory. So maybe you could think of the other agent as a database, right? You'd say, hey, please pull this from memory for me, right? Okay, so in that case, they acted like a database, right? So there was a read-only operation that happened there. Yeah, but basically it's RBAC on everything. So we can do, it can be whatever. It doesn't have to be read write. We can do whatever. So, okay. So So the DID. GitHub exec, DID, GitHub exec, PDX Johnny. And so what we're going to do is we're also going to overlay all of the SigStore verification stuff on this. And so we're going to import all of that information into this space, right? So we're creating basically like all we have to do, all we're saying is that if you serialize, if you speak DID and peer DID, then we can speak supply chain security to you, right? Because we're going to proxy all the tools we know about, and we're going to generate all the data that we can, and we're going to throw it all into this format, right? So if you speak this format, then sweet. If you don't speak this format, then boom, we're going to call your API, and all of a sudden, boom, now you speak this format. Congratulations. Everybody speaks this format. These folks did a great job. So, all right. Okay, so let's execute some code. So let's pretend we have a repo, https github.com/pdxjohnny. Oh, SSH keys are back. Access restrictions on branches. Yeah, okay. So I think we're just going to basically separate these. Let's call it HTTP test, right? Because that's here we have something. And then let's say, what's HTTP test at these days? Um, uh, One point five point one. Okay. 1.5.1. All right. No, so let's say DID. Oh, right. Example GitHub exec supply chain security. Right. So everything. So why do we care about this, right? So if everything can speak this language, then all of our, so we from the perspective of the DFFML project, right? So if we can help make it easier to talk this format, then that's a good thing because we believe that people should communicate effectively, and effective communication comes from having shared patterns and shared languages, and this DID is an effective primitive for communication. And so it seems as if it could be applicable and used in its maybe not in its so there's maybe there's specific algorithms or something, but the conceptually, right? Uh, Conceptually, this is a great format for building chains of trust. Um, and we can have intermediate formats wherever we want and represent the data in the same way, for things that may not support this directly, but it's a nice shared format that we can proxy between systems, and systems can have their own internal representations of identifiers, just like different static analysis tools and stuff, right? So let's just write this to a file. Okay. Okay, so example of dependency swap, dependency hot swap. Okay, so build comes in. So now remember, the open architecture allows for is effectively, we're proposing a methodology for interpreting different domain specific architectures, and knitting together the interpretations of different domain specific architectures in a shared intermediate representation, which one very good option for doing that, which we suggest, is using DIDs and peer DIDs and such. And as a serialization format for this intermediate representation, right? So leveraging this intermediate representation, it becomes very easy, right, with DIDs, at least this notion, right? So DIDs are a great serialization format with it for this, but this notion of distributed identifiers in general, whether you want to write them like this or whether you want to put it in a byte string format or whatever the hell you want to do, but conceptually, this DID stuff. Um, Allows us, however you want to serialize it, allows us to build these intermediate representations of architecture, right? And then we can apply because, if you should choose a serialization format or, serialization and deserialization flow which supports the understanding of the provenance information that needs to be involved and cryptographic assurances as a part of that, right? So DIDs provide that for us, which is why we're just going it with them. This is great stuff. So okay, so example of dependency hot swap. Okay, okay, so let's just do this. Okay. Let's just say this key is for HTTP test and it signed the 1.1.5 commit or maybe like uh, enter or let's see no okay so you need to so HTTP test 1.5 signer. Okay, so basically, so this is the key for, um, okay, so this is the key for the HTTP test project, right? And then the key for the project, once again, we're just building these trees of keys, right? So we'll have to figure out revocation. So I think revocation will just I think revocation is a context-aware thing. So if we know that we're supposed to be going to GitHub, then we'll also have an overlay that says, "Hey, go check the GitHub revocation. Stop before you import any of these things unless you've checked revocation." So it should be pretty straightforward. Um, okay. Yeah. So this basically says I'm the signer, right? For 0.155 whatever. And this says, where's my okay, zero point 0.4. Right. So say maybe we have this, you know, colon separated list of, let's actually do a slash separated because you'd be hard pressed to find something that puts a slash in a version. So yeah, let's say, so these things, it's just, I mean, and this is just completely arbitrary. The whole point is that you can do whatever the hell you want. So then you look over here and you just do a lookup, right? So you see where I'm typing is here and here. And let me just make these keys a lot smaller so that you can see them better, right? Okay, so now you can see those keys better. Or you can see okay, so C lookup table in like dot keys, right? Was it dot keys? It was dot keys. Okay, fantastic, right? C lookup tag, C lookup, I don't know, this, lookup that, right? The DID, lookup, Shawnee in, then, okay. So we, uh, Okay. So we look up PDX shiny within blank. So and this example, example of dependency hotspot blank. Okay, so for HTTP test, so look up PDX shiny within github.com PDX shiny keys. Okay, so we see it's here. Uh, split on slash or yeah. So search each key comment for one that starts with um, the uh, with HTTP test slash behind the slash split on slash uh, to find the keys for each release, keys which signed each release. And so then here we go, we have a ED ED25519 key, which is an SSH key, right? And so these are keys which were used to sign particular releases, right? Now these keys we could do, right? So this is a naive example where we look up in the same file. So basically any key that we've uploaded to GitHub, right? But we could of course have another indirect jump where we say, okay, maybe you split on slash, and then the first thing is actually the repo name where I'm going to store all my keys, and then I can just go over there, right? But it's because I already am all within the same domain of trust within GitHub's HTTPS service, right? So I think this thing is reflecting in my eye, maybe. So I'm going to stop this now. Whoa, okay. So okay, okay. What time is it? It's 9. Okay. Okay. So what do we do now? Okay, so TPM TPM to ED25519. Come on, come on, come on, come on, come on, come on, come on. Give me a key. Come on. Come on. Do it, do it, do it. Come on. Shit. Oh, it doesn't matter. It doesn't matter. It doesn't matter. What the hell am I doing? It doesn't matter. It doesn't matter because we're going through. Okay, so those SSH keys, we don't need them to be. The only thing we needed to be the ED key was, um, the only thing we needed to be the shared key was that GitHub key. So we mint, we, fuck, we mint, fuck, uh, we, we generate a ED25519 key, which we also do Filippo's trick, which is in libsodium, to turn into an X25519 key, and then we do we even need to do that? Actually, no, we didn't even need to do that. We didn't even need to do that. Um, we didn't even need to do that because, oh shit, we don't even need to do that because the, do we need to do that? No, we do need to do that because we do need to do that because we'll use that to create this basically what it exists almost like a verifiable credential or an ephemeral. Yeah, I guess it is a verifiable. It's a peer DID. It's an association. It's basically like, hey, you know that I'm linked to you, and I'm like, it's like I think it's a verifiable credential in this case, but I think we're effectively going to have it be a peer DID. Um, and so we do this thing where we have both the ED key and the X key, and so one you can use for signing and one you can use for encryption. And usually we don't reuse keys for signing and encryption, but this is a single purpose key which exists only to uh, to is it really a single purpose key? It exists there. So it exists in GitHub only to be verified as the public. It exists within, yeah, it's a single purpose key. GitHub is just the public portion. Okay, and then from the public portion, when we do the lookup, it allows us to determine, okay, but is this signed data here? No. But we trust that this is the public. We trust that this is where we can get the public portion from because we trust GitHub. So we trust that this is the correct data. Okay, so we don't necessarily need to sign it, but we could if we wanted to. Kind of doesn't make any sense because then we should have signed the key in the first place. Well, we are signing the key because the key is the same. We're not signing the key. We don't have to. It's the key, same key. Um, but anybody could upload the public key. Anybody could upload a public key and say, this is the key for this release. Okay, but they can't do it for your repo. You're only doing it for your repo. So basically, if you look up HTTP test, this says this has to be this key that signed this release within this person's repo. So you're not going to be playing any tricks. So so basically, this lookup goes through here, says, okay, we've got the key, we've got the right key. So basically, we generate this. Where did we go? Okay, so HTTP test. All right, so we go here, and then maybe we uh, maybe there's something else, and then we like parse the body and we figure out which one for this specific type of GitHub DID, right? Like maybe we even said GitHub release body parser number 35, right? It's completely arbitrary, right? It's the whole thing is like this is a data flow that you're deciding to execute. To deserialize an input DID, right? This is the whole point, right? Input DID comes in, we're within an operation within the input network, we're deserializing the DID. What is the value, right? Okay, so because you just got the ID, that's all you got in this case. What is the value? Okay, so this is how you're doing the lookup of the value in a cryptographically secure way, right? And then you can also do replacement on it because if you're always storing these things as DIDs, you can swap out wherever you want, but because you're using a shared serialization. Okay, I'm not going to do the rest of this example. Is this is the chain of trust. You look it up. That's the point. It's just a lookup table. And the key is yeah. Okay. Okay. I need a break. I gotta. This